Okay. Anyway, so remember we actually spoke about frequent pattern mining very briefly at the very first lecture, right, where I was introducing different machine learning tasks to you, right. So this is a form of unsupervised learning, and the statisticians call this as, I told you that also. Statisticians call this as bump hunting, right. So you have a remarkably flat probability distribution, okay, then there are small bumps somewhere. So what does it mean? They are slightly more frequent in the data than the rest, right. So that is essentially what bump hunting is. So I have a very large base, right, I have an exponentially large set of possible outcomes, right, and I am going to have an extremely low probability of seeing any one outcome, right, but there will be small bumps here and there which are places which are slightly more frequent than what I would see normally, right. So what in the modern context, right, so something like Amazon's logs, if you look at who bought what on Amazon, right. So if you think about it, Amazon has millions and millions of transactions, right. So say suppose they have in a month, let us say they have like 10 million transactions on Amazon, right. If somebody bought say 10,000 copies of the same item, not somebody, like some item was sold 10,000 times on Amazon, right, that is a very frequent occurrence. But think about what fraction of 10 million is 10,000. One percent, 0.1%, 0.01%, 0.1%, right. But that is why I call this bump hunting. It is remarkably flat, right. So I have a huge inventory in my Amazon base, Amazon catalog has a huge inventory, right, and I am looking for frequent items there, which will be like something sold 10,000 times is frequent for me, even though the overall transaction is like 10 million, right. So this is essentially what I am talking about when I talk about frequent pattern mining, okay. So it is you have to take the frequent part here with a pinch of salt, right, but all the examples and illustrations I will give you, a frequent will be like 50% of the data or something, okay, that is because I can't draw 10 million things on the board, right, but in reality when you actually use these kinds of things, the numbers will be, the fractions will be very different, okay, just keep that in mind, okay, right. So I am so frequent patterns are those that are above a certain suppose above a certain minimum support that I am looking for in a. So what is the support of a pattern in a database? That is the support count, okay. So support of an item is essentially the fraction of times it occurs, right. So take the support count, which is the number of times it occurs, divided by the total number of items, it gives you the support of the item, right. So I will call an item as being, or I will call a pattern as being frequent if it is above the minimum support. So minimum support is a parameter that I define.
It's less than 1.
I'm sorry?
It's less than 1, it's a fraction.
It's less than 1, it will be less than 1, but it's a parameter that I define, right. So occasionally what people do is they actually translate the min support also into a count, right. Essentially you take the fraction, you multiply it by the total number of items, it gives you a count. It is sometimes easier to think of it as, okay, I have a transaction of, say I have a total database of 10 possible transactions, I will look for a min sup of 2, right. So that is like 20%, so but then you could think of it that way as well. So min sup is essentially the minimum support level at which I will consider something as frequent, right. So classically, right, frequent pattern mining was applied to transactional databases. So where I have a collection of transactions, right. Transaction essentially could be things like, okay, these are the items you bought together, right, or these are the items you checked out together from a bookstore or a library, Okay, these are the items you borrowed from a library together, some kind of a transaction. So something went from A to B. Okay, so that is the usual classically where they applied this, right? And as you were mentioning, market basket analysis is a place where they did this first, right? So why it's called market basket analysis? So you go to a shop, right? You go to a supermarket, you buy something in a basket, right? You generally tote a basket along with you. You start putting things from the shop into the basket, and then you come and get it checked out, right? So everything that goes together into the basket, okay, so we call it single transaction, right? You might buy some cereal, you might buy some milk or whatever you want to buy, right? Some vegetables, everything you put together and you bring it to the bill, right? So all those things that go together we call a transaction. So market basket analysis is essentially analyzing what goes into your basket, right? So this is the kind of things we will have, right? And so these transactions will essentially be defined over a universe of items, right? And each transaction will be thought of as a subset of these items, right? Or as the data mining people call it, will be referred to as an item set. Okay, so what is an item set? It's a set of items, that's it. Okay, so instead of calling it grammatically correct fashion a set of items, okay, for whatever reason they introduced a new noun called item set. It's a single word. Okay, they introduced a word called item set, and then they started calling it frequent item set mining and so on and so forth. But so we will typically be using the word item set and and we will also use a term K item set. What do you think is K item set? Set of size K, set of items of size K. Okay, that is a K item set, right? And yeah, so what else? So we also have something called association rules that we talk about in the context of frequent pattern mining. So what is an association rule? These are rules of the form A implies B. What does it mean? It means that, okay, if you buy items in the item set A, right, then you are likely to buy the items in the item set B. So A and B are sets, they are not individual items, A and B are sets, right. So if you buy things in the item set A, so for example if you buy the usual thing offered is if you buy milk and bread, you are likely to buy eggs or something. So you are basically going out shopping for breakfast items, right. So you buy milk and bread and then you also buy eggs, right. Also a very famous or infamous example that people had. What's it? Yeah, if you go out to buy beer, you also buy diapers. So why you think that is? Causal effects? You're kids, you're not supposed to know this. Don't laugh at this. Yeah, some of the masters and PhD students can laugh. Okay, I'm just kidding. Hey, so yeah, so why do you think that was the case? Any theories? Come on, it should be given. Give me some theories.
Then you have hair turn. After all that, you're like.
Man, people have been giving you horror stories about having kids, huh? It's not that bad. So there was another. Then people did some analysis and they actually found out this spike was happening on Sundays, right? So in the US, Sunday is football day. Right, every Sunday they have football playing. Okay, these guys are actually buying beer. okay, to drink during the watching the football game. So at the same time they also pick up diapers because they don't want to be disturbed by the baby during the game or something, right. So they probably slap a couple of diapers on the baby and then say, okay, don't call me while the game is going on, okay. So that's basically what was happening. Of course it had anyway. So that's a larger point to this, right. So it's not enough for you to do association rule mining. So some of the associations you discover just from the data might not immediately have any meaning to you. For example, you can't say buy two crates of beer and get a diaper free or something, right. So you can't use that for promoting sales, right. Or also it will look really weird if you start stacking diapers next to the beer cans in the shop, right. So some rules are used. I always use that example to illustrate the fact that, hey, statistics is all fine, right, but you need something more than statistics in order to get any useful intelligence out of data. So you need to think of other ways of doing it, but we are not going to do that, right. Great. So how do I know this A implies B is useful, other than, I mean, ignore the discussion we had, right. Normally how will I say whether it is useful or not? So I have different measures by which I can measure the usefulness of a rule, right. So two most popular ones are called support, right. So what do you think is support? How many times? A and B have occurred together, right. So this is essentially the probability of A union B. So A union B is like set union, right. So how many times A and B have occurred together, right. And the second thing that we look at is what's it?
It's the number of times both A and B has occurred.
Yeah.
Why A union?
It's set union.
Set union, yes,
So A is a set, B is a set, right. So when you do the union of that, so all the elements in A and B, what is the probability that all the elements in A and B have occurred? This is how it is usually denoted, right. So it's a set union. So if this had been literals, right, then I would have put A and B. What's the probability of A and B? But since this is a set, I do A and B, okay. And confidence is essentially the probability of B given A. I am saying A implies B, right. That means then I have to figure out, okay, how many times did B occur when A occurred, right. So this probability of B implies for A implies B is confidence of A implies B is probability of B given A. So this is essentially the number of transactions having right. So number of transactions having A union B divided by the total number of transactions. This is the number of transactions having A union B divided by the number of transactions having A, okay. So how do you find these association rules? You first do frequent pattern mining, find all patterns that are frequent, right, find all patterns that are frequent, okay. Then you will find that, okay, A is frequent and some A union B is also frequent, right, and then from that I can start inferring these kinds of association rules.
But finding all patterns will be very.
Finding all patterns that are frequent. But yeah, you are right, but it's still a hard problem. So that's what the rest of the class is going to be about. How will you do this efficiently, right? So usually how you do this is the first step is find all frequent patterns. Second step is infer strong association rules, right. So all frequent patterns or item sets, right. Let us get into the habit of calling patterns as item sets, right. So all frequent item sets are item sets which have min support, right. All strong association rules will be those association rules which have min support, right, and as well as a min confidence, right, minimum support and a minimum confidence. I want both, right, for a strong association rule, but there is a caveat, right. Just having strong support and strong confidence alone is not enough, right. So you will also have to see what is the probability of B in isolation. I look at probability of B given A and I say it is 0.6, okay, that looks like a good association rule, but if I remove A, I just look at what is the probability of B, and if it's, I say the probability of B is 0.75, right. So what happens? A implies a depression in B actually, right. I should not say that if A occurs then B will also occur. If A occurs then the chances of B occurring will go down, right. So this is something again a classical example is when people are analyzing data from a store called Blockbuster, right. So Blockbuster rents videos, they also sell video games, okay, and they found out that if people rent videos from the shop, I am sorry, if people buy video games from the shop, they also rent videos. That rule had a confidence of 0.6, right. But then if you do not buy a video, or if just anybody who comes to the shop, whether they buy a video or not, I am sorry, buy a game or not, right, that is a probability of 0.75 of them renting a video. So essentially if you go to the shop to buy a game, you are less likely to rent a video, right. So you have to be careful about that, right. So there is another thing which people use, which is essentially the ratio of these two things, right. So if this is greater than 1, then knowing A is useful, right. If it is less than 1, then knowing A is not useful, okay. This quantity is sometimes called lift, okay. So lift also has another interpretation. Sometimes people take the difference between the two and that is also known as lift. Sometimes people take the ratio. I think nowadays ratio has kind of become the standard way of defining lift, okay. Right. So and I should tell you that association rule mining is a very popular subfield of data mining, and I given you 3 different ways of measuring usefulness of rules, and there are about 100, right. And I do believe Nandan covers a good fraction of those 100 in his courses, right. So if you want to know more about it, go to DOMS, right. So but there are lots of different ways of measuring that, but these 3 are pretty common. Support and confidence are the base, right, and then people build a lot of things on top of support and confidence, okay. So that is basically it. So I am not going to talk about association rules anymore, right. The interesting problem, as you would have rightly surmised by now, is finding all frequent item sets, right. So just a couple of other definitions here. an item set X is closed in a particular data set D if there is no superset of X that has the same support as X. Okay. So it has to have a lesser support than X. Okay, then you call that a closed item set, right. What is a frequent closed item set? So closed item set whose frequency is higher than min sub, right. Right. So if I give you the counts of all the closed item sets in my data set, I am sorry, all the frequent closed item sets in my data set, right, you can recover the counts for all the frequent item sets in the data set. Right, if I give you the counts for all the frequent closed item sets, right, you can recover the counts for all the item sets in the data set. It is kind of fairly straightforward, right, because when would the item set be part of the closed item set? If a superset has a lesser count than it, right, but the superset could still be frequent, right. Let us say I have a frequency threshold of 2, right, and some item set has a count of 5, and add one more item to it, it has a count of only 4, right, but still that is also frequent. It will be part of the closed frequent item set as long as there is a superset of that has a smaller count, right. If it does not, what does it mean? If I say that ABC is a closed item set, right, and there are no 2 item sets that are closed, what does it mean? The count of AB, the count of AC and the count of BC is the same as the count of ABC. Do you get that? So if I say that ABC is a frequent closed item set, right, it is a frequent closed item set, that means that and it has a count of say 5, and that means that AB is also a frequent item set, right, AC is also a frequent item set and BC is also a frequent item set, and what are the counts of AB, AC and BC? 5, right. So if I give you the frequency of all the frequent closed item sets, then I can recover the frequency of all the frequent item sets, right, that need not necessarily be closed. Right, that is the reason it is called closed. So essentially this is sufficient for me to recover the entire data, right. So typically if you are trying to come up with a new a new counting algorithm for item sets, right, you have to make sure that you return the closed the complete set of closed frequent item sets, right. Right. Item set X is a maximal frequent item set. If X is frequent and nothing larger than X is like any no superset of X is frequent, right. So it is a severe case of closed, right. So closed, what the closed condition is, the superset should not have the same count, right, should have a lesser count than the subset, right, but it could also be frequent. Here I am saying not only should the superset have a lesser count, but the count should be so less that it is no longer frequent. Okay. So the set of maximal frequent item sets will be smaller than the, right, the set of all maximal frequent item sets will be smaller than the set of all closed frequent item sets, right, or frequent closed item sets. So that will be smaller, and is the maximal set sufficient for you to recover all the frequent item sets? No, not necessarily. Sure.
Every subset has greater frequency.
Sorry.
Every subset has a greater frequency than X.
We didn't say that. Subset could have a lesser frequency. I mean equal frequency.
Greater than equal. So
Ah.
all of those are also frequent.
Yeah, but I can't give you the frequency of those. But I can say which are all frequent, but I can't give you the frequency of those subsets. While in this case I can give you the frequency of the subsets because they will be the same, right. So I can still recover something about the frequent item sets, but I will not be able to tell you what is the frequency.